All right, this is going to be our last video on the Unit 4 Physics Study Guide. I'm going to be working on the centripetal force and uniform circular motion questions. There are, I think, 5 of these. 3 of them are short, 2 of them maybe a little bit longer. Looking at question 13, it says, what is the centripetal acceleration of an airplane traveling at 350 meters per second in a radius of 10,000 meters? Ooh, it may seem like that's a really big radius, but planes take very wide turns. So we are going to be using this equation. Our centripetal acceleration is going to equal velocity squared over the radius. Plug those numbers in. 350 meters per second squared divided by 10,000 meters. And what I want us to notice about our units, these would become meters squared per second squared. And then when we divide it by meters, it becomes a nice meters per second. So 350 squared gives us a big number, 122,500 meters squared second squared, divided by 10,000 meters. And I'll just write the answer down here. The acceleration would be it's pretty high. 12.25 meters per second squared. That airplane's pulling over 1G. That'd be a little bit uncomfortable for a full-sized commercial aircraft. All right, next question. If a person is running in a circle with a radius of 5 meters, what must their velocity be to feel the centripetal force of 9.8 meters per second? So we are running the exact same equation here. The difference is I'm asking for velocity. So I'm going to be solving for my v. I know my acceleration, 9.8 meters per second squared. I know my radius, 5 meters. We're going to multiply both sides by 5 because that's the opposite of dividing. And once I multiply both sides by 5, I will get the v squared equals 49 meters squared per second squared. We're going to take the square root of both of those, and we get a perfect 7 meters per second. All right, next question. A 0.3 kilogram ball attached to a 1.2 meter string is being swung in a circle. What is the net force on the ball if the period is 1.5 seconds? So let's draw a quick picture of what this kind of looks like. You got a center point here, and you got a string attached to a ball with a mass of 0.3 kilograms. It is being swung in a circle around, does not look like a perfect circle. In a circle around this string. So the string is the radius, 1.2 meters will be that radius. And it takes 1.5 seconds to go all the way around. I think I got all the information there. So the force, your net force, is going to equal mass times your net acceleration. And this, let me remind you here, centripetal force is a net force in a problem. So we could have easily said, what's your centripetal force here? And this acceleration, you could write centripetal acceleration or net acceleration there. So we know the mass, so we can plug that in. We just have to find our acceleration here to plug it in. So we are given a period. So we're going to write that equation down to find acceleration. That would equal 4 pi squared r divided by t squared. T would be that period. So just by plugging in some numbers, 4 pi squared, r is 1.2, and t is 1.5 squared. Plug all that in your calculator and we'll get a nice number here. 1 second. 4 times pi squared times 1.2, and then we are going to divide that by 1.5 squared, and that should give us about 21.1 meters per second squared. So we plug that into this over here, and we'll say F net equals mass 0.3 kilograms. Make sure you're using kilograms whenever we use force, because newtons are kilogram meters per second squared. So I gave you kilograms here, so you don't got to worry about it. But if I gave you grams, you got to convert to kilograms. And then you just plug in your acceleration, 21.1 meters per second squared. Multiply those two numbers together, and you get something like 6.3 newtons. All right, there we go. Look at that. First 3 done. I think we got 2 left on the backside. A 50 kilogram person goes on a roller coaster which has a perfectly circular vertical loop with a radius of 8 meters. The roller coaster has a velocity of 21 meters per second going through the loop. What is the normal force felt by the person on the top and bottom of the loop? Okay, let's do this. So first thing that we got to think about, and here I'll draw a little circle here. In this roller coaster loop, we're going to be feeling different forces. We're going to be feeling our centripetal force. That's going to be the net force. And it's always going inward. And it should be equal the whole time. So sorry, those should be equal. But on the top, we have gravity. I'm writing this very, very small here. That's gravity. And we also have the normal force. And when you add both those together, it's going to give you the centripetal force, because the centripetal force is your net force. So when we say the normal force felt, we're getting asked for Fn right there. And similarly, on the bottom of this roller coaster, gravity is still going down. So when we add the gravity and the normal force actually has to be greater than the centripetal force on the bottom, because it has to be normal force plus gravity has to be that centripetal force. So that's how we got to be kind of looking at this, from the top of the loop like this, and from the bottom of the loop, we got to look at it like that. I have this equation that I worked out. You guys have this in your notes. The normal force is going to be equal to the centripetal force minus your force from gravity. So we can simplify it a little bit more. And again, you have this in your notes as well. That would be your mass times your centripetal acceleration minus gravity. And now we can use this equation to solve two questions, from the top and from the bottom. First, we're going to start from the top. We'll do the bottom later. We'll save this spot over here to solve for the bottom. So we'll write that equation down. And when we're looking from the top, I want us to really think about our perspective. Gravity is working in the same direction as the normal force. So it's going to feel like a positive acceleration in this problem because we're going to turn our coordinate system completely upside down because we're going to feel like we're upside down. So when we plug our numbers in, our mass is 50 kilograms. Our velocity is 21 meters per second. We're going to square that. The radius is 8 meters. And the gravity is going to be a positive 9.8. And we're subtracting it, so it'll be, minus a positive number. So we will simplify this a little bit farther. It will be the 50, 21 squared is going to be 441 divided by 8. About 55.1 minus 9.8. And we could simplify this farther. 50 times 55.1 minus 9.8. And we get 50 times 45.3. That's still a lot of force. Wow. 50 times 45.3 equals, that's not going to be a comfortable roller coaster, especially at the top. 2,265 newtons of force on the top. Now on the bottom, we are going to be doing exactly the same thing, except in this case on the bottom, gravity will be going down, so we have to use a negative number for that. So plug in some numbers in. Mass is the same, 50 kilograms. Velocity is the same, 21 meters per second. Square that whole thing. Radius is the same, 8 meters, minus, here's the big difference, minus negative 9.8 meters per second squared. And we know, we multiplied all that together before. We know that this equals 55.1, but in this case, we are adding 9.8. So our normal force would be 50 times 64.9. This is a lot. Times 50. 3,245 newtons. That is not a comfortable amount of force to feel. All right. And for our last question, we got a question that kind of involves friction. A little bit of a tricky question, but it's not anything we haven't seen before. We can do this. So a 500 kilogram car racing on a flat racetrack is traveling at 36 meters per second around a curve with a radius of 150 meters. Find the car's centripetal acceleration. Then what is the minimum coefficient of static friction between the tires and the road to prevent the car from slipping around the curve? All right, so first let's get that centripetal acceleration that we need. We have the velocity and we have the radius. Easy to plug those in. So 36 meters per second, square that number, divide it by 150 meters. And you get about 8.64 meters per second squared. All right, so that is your centripetal acceleration. So next, when we want to find our centripetal force, real easy. You just take your mass and multiply it by your centripetal acceleration. That is going to be 500 kilograms times 8.64 meters per second squared. Or this force is going to be 4,320 newtons of force. So the next thing we got to think about is if we want to find our coefficient of static friction, we have this equation here. The equation is your force of friction is going to equal, your coefficient of static friction times your normal force. Your centripetal force is going to equal the friction needed. You just have to find your normal force. And remember, that's just going to be, it's flat. You're pushing up against gravity. So it is going to be your mass, 500 kilograms, times your gravity, 9.8 meters per second squared. So Fn equals 9.8 times 500, 4,900 newtons. Now we have everything we need to plug into our equation here. 4,320 newtons equals our coefficient of static friction times 4,900 newtons. Divide both sides by 4,900, and we get our answer 0.88. And there's no units here because the units all cancel out. So if we are understanding these centripetal force questions, we should be feeling pretty good about the test coming up.